So welcome to the Advanced Statistical Physics, Physics A310. It's a lecture 2 of the course. It's the thermodynamics of photon gas, the bimodal of solids. Next slide. So this is a brief contents of lecture 2. I will start with summation rule for acoustic phonons in solids. Consider their thermodynamics. And then I will derive for you the Y formula for thermal capacitance of solids. I'll consider limiting cases of this formula. It leads to equipartition in classical case. And I'll compare it to photon gas in quantum case. And that would finish the substantive contents of this lecture, but there will be a bonus part. In section 5, I will give you a brief history of Peter Debye in the framework of his time tribulations. It is a remarkable life, remarkable history. And history is important because, as old saying goes, those who do not remember lessons of history are destined to repeat its mistakes. That's what we don't want to do. Next slide. We'll start with the general formula for internal energy of bosons. Why bosons, I'll show you in the next paragraph on the slide. Why phonons are bosons, just like photons are. So this general summation formula, this internal energy is sum, we know it, over all states in the Hilbert space. And we know how to do it for momenta, and that will be momentum will be continuous coordinate. This is the energy of a particle in the state J, mu is chemical potential that controls the number of particles if it is conserved. If it is not conserved, a particle like photons and phonons for that matter can freely be emitted and absorbed, the mu should be set to 0, which we will do. Kb is Boltzmann constant. This temperature. For bosons, we'll put here -1. For fermions, would have had +1, but in this lecture, we'll be dealing with bosons. Again, J is index denoting state of one particle. In our case, J consists of two components. P is a momentum, which is a good quantum number, is a conserved quantity for uniform space, where we assume our gas is contained. And sigma denotes polarization of a phonon. So what kind of polarization we can expect of phonon? So phonon is created by displacement of atoms. And the wave of this displacement consists of displacement periodically repeating in state, in space, and changing harmonically in time. And there are three directions of displacement. So one direction, which I will denote by 1, here, it is, ours will start with direction of displacement in the direction of propagation of the wave. So it's direction of P, momentum or related wave vector. So if you think about atoms displacing in the direction of propagation of the wave, obviously that creates the region of high density and low density, compressions and decompressions of the matter. So it is a wave of density. That's called longitudinal wave. The displacement is in direction of wave vector, or momentum of the wave. To other polarization corresponds to displacements in the normal direction with respect to direction of propagation. So this so-called transverse phonons. And if you think about displacement in direction normal to propagation, such displacement do not create modulation of density. They create distortion of the unit cell of the crystal. Unit cell has certain rigidity, and that creates the restoring force for oscillations. However, that should be crystal to create restoring force. So in a liquid or in a gas, there is no such thing, the distortion of the lattice, and these two polarizations do not exist. So in the gases or liquids, there's only one phonon, which is longitudinal phonon, and no transverse phonons. However, in a crystal, which has rigid unit cell, there is such a force, a restoring force, and we have three phonons, generally different. In general case, the longitudinal phonon and transverse phonons have different frequencies. In isotropic crystals, say cubic crystals, the two transverse phonons will have the same frequency. They will be degenerate. However, in general crystals, that is not the case, and all three phonons will have different frequencies. Keeping this in mind, we'll try to understand what is the summation of a state of a particle in a Gilbert space, given by P and sigma. So what's shown here, as we do, is any expression that depends on J, particularly this expression. So this is sum. J is two component, sum of sigma, of polarizations, and sum of momentum. And this expression depends on polarization and momentum. So the summation of polarization will leave as it is. We can do anything here. The discrete variable 1, 2, 3. But this summation of momentum we know how to do. It is volume multiplied by integral of over momentum of this or any other expression that depends on momentum. So they present it as a function of momentum now. And we should divide this by 2 pi h cubed. So this has very simple physical meaning. 2 pi h cubed is a unit of volume in the configurational space of unit of physical system, one particle. V is integral over momentum, over coordinate, and system is uniform. So this integral gives me volume, multiplied by integral over momentum. So this integral over coordinate, integral momentum, is an integral over all configuration space of the system. So this 2 pi h cubed is unit of the volume in the configurational space. So this is really a summation of a configurational space of the system in a quasi-classical approximation. So when instead of summation, we have integration. This is very good approximation for systems not very small. Having said this about fundamental properties of this expression, now let us simplify it further. We will be using the first assumption of the bimodal. This assumption is that the dispersion relation of acoustic phonons is linear. So energy of acoustic phonons is h omega, of many phonons h omega, when omega is frequency, general relation between frequency and energy in quantum mechanics. And this is linear relation means that this coefficient between momentum and energy. This coefficient has dimensionality of velocity, and easily you can see that it is velocity, the phase velocity of the wave, which is a derivative of it's a ratio of the energy over momentum. From this relation, we can find momentum as a function of frequency. So P is h omega over c sigma. Now we understand when we will substitute this P here. This is 3P, it contains cube of P. So we'll give in denominator cube of of phonon speed, C sigma, I will get third power of h, and the third power of h will cancel completely this third power of h. And also this integration over the angle will give me 4 pi, which will cancel 4 and pi of this 8 pi cube h cube. That it will give, we'll get on the next page. So we come into the next page. This is this expression. This is cube of phonon and speed of phonon is polarization C in denominator. This is this integral I was speaking about, d omega omega squared. So it was cube of momentum. This expression now has to be presented in terms of the frequency. However, here is difference from photons. For photons, here would be infinity, because the maximum allowed frequency of photon is infinity. There's nothing that limits frequency of photon. So frequency of photon goes from radio wave to microwave to terahertz to far infrared to mid infrared to near infrared to visible, go through red to blue, go to ultraviolet, then go to X-rays and go to gamma quantum, go to infinity. There is no physical limit to the frequency of photon. However, for phonons, such a limit exists, because this dispersion relation between momentum and frequency. Momentum in crystal is limited by the size of Brillouin zone. It cannot go outside of the first Brillouin zone. And therefore, because momentum is finite, maximum frequency is finite. And this maximum value of frequency may depend on polarization. Therefore, I will put here as a limit certain frequency, its maximum frequency of the phonon for all three polarizations. So, at this moment, I finish certain part of this lecture. So up to the formula 3, I will break for 2 minutes. I will let you ask questions. So we already used one of the approximation of the bimodal. It is linear dispersion relation of acoustic phonons that is limited by certain maximum value. Now, the second simplifying approximation is the following. There's a maximum frequency omega sigma d actually does not depend on polarization. So it is just one frequency, omega d, is a parameter which is called the bifrequency. It is not, by no means, is an exact statement. It is not even an approximation. It is a what called model. Model is not necessarily is approximation, reasonably obtained from first principles. It is approximation to allow you to obtain solution. And then you can compare a solution to experiment, and if it satisfies the experiment well, this model will live. And the bimodal is exactly that. It actually agrees with the experiment very well. The physical reason that we can use this approximation is obvious. To the same extent as the dispersion relation is linear in the entire range of momentum, which is not true, that certainly would be violated at the boundary of Brillouin zone. It can only be considered linear if only phonons with relatively small momenta contribute. But if phonons with small momenta contribute, then also it does not matter what is the maximum frequency. We never reach that area of dispersion relation. It is enough to put one frequency, but we should have one frequency. That I'll explain in the next slide. We cannot put this frequency infinity. So having said all of this, when I neglect dependence on frequencies here, this expression becomes expression only, it depends only on energy. So now it will depend only on frequency, it won't depend on sigma at all. The only dependence on sigma was here, and by the bimodal there is no such dependence. So the summation over 1 over sigma can be affected independently, and that will show you. So rewriting this expression, so v of 2 pi squared that was left after I made my substitution and cancelled for pi from integration of d3p. Now I take this sum and surround by parentheses, which needed only to guide I, so now this sum can be done independently. It's just a number, dimensionality of inverse cube of velocity. And I have integral of omega to some limit omega d, and explain on the next slide why I need omega d, cannot go to infinity, of the expression that I need to sum, that now expressed in terms of the omega, frequency omega. Now I'll explain you why you cannot set maximum frequency to 0. It's a finite parameter that you need to find. You may calculate, but better you compare it to experiment and you find it. So how do we find it? Photons are oscillation electromagnetic field, and each frequency corresponds to independent degree of freedom, independent oscillation. There is infinite number of these degrees of freedom. Have in a crystal, total number of vibrational degrees of freedom is fixed, is finite. That is equal to the number of degrees of freedom that atoms have, because the oscillations represent the translation motion of atoms. So each atom has 3 degrees of freedom, corresponding to displacements along x, y, and z. So the total number of degree of freedom of atoms in solid is 3Na, where Na is the number of atoms. Therefore, if I, by my summation rule, sum 1, I should get 3Na. Now let us go. This is summation rule. I repeat it here. And put 1 here and put 1 here. So this will sum over 3Na. This is this rule. And here we'll give a trivial integral, which I can affect immediately. This omega cube d over 3. So I put omega cube d over 3 here. And from this I can find this coefficient, equating right hand side to left hand side. So this is this coefficient. So the 9 was 3Na and was omega cube d over 3. So over 3 goes to numerator, give me 9. So this is this coefficient. I'll take this coefficient and substitute it back to the summation formula, removing the velocity, the speed of sound for 3 polarizations. So instead of this, I'm putting 9Na over omega cube d, and I'll get summation rule, which is extremely simple. So sum any expression that depends on quantum number of one particle, I need to integrate to frequencies that represent its energy, from range to 0 to omega d with weight omega squared, and the coefficient that determines the number of degrees of freedom of the crystal is 9Na divided by omega cube dBi. Omega cube dBi is a free parameter of the theory. So before going further, let me suggest you to ask questions, whatever was before. If you don't understand something, or you have alternative explanation, or you want to argue with me, you're absolutely welcome to do it now, in the next 2 minutes. Let's go. Repeating this sum rule that the last page, last slide ended. I'm just repeating it without changes. When I repeat, I always give original number of the formula. Now we need to build thermodynamics based on this formula. We just need the summation formula. And you already know shortcut to thermodynamics. It's not calculation of the Landau potential or grand potential, grand canonical potential. It's calculation of the internal energy. So this internal energy of the system this expression we already had at the beginning is formula number 1. Now I'm using this summation rule. I will write this summation as a number. It is coefficient 9 Na divided by omega cube d. This epsilon is h omega. So I get an extra h here from h omega. The summation itself has omega squared d omega. Extra omega from energy give me omega cube d omega. Energy of the phonon is h omega. This kBt is from the distribution. Chemical potential is set to 0 and -1 corresponds to bosons. So we got an integral that we need to simplify. Let us do it. I'm repeat this last formula without change. And always simplifying such integrals that contains transcendental functions. We take argument if this single function, a function has the single, maybe several functions, but they have a single argument. An argument is h omega over kBt. You need to make this argument a new variable. It's a dimensionless quantity, of course. You need to make a new variable, so we introduce variable z equal h omega over kBt. And that implies that omega here is equal to kBt divided by h multiplied by z. If d omega has the same coefficient. So this coefficient will come to the fourth power. Third power from omega cube, first power from omega. So this coefficient, kBt over h, comes in the fourth power. Upper limit of this coefficient will be h omega d divided by kBt. This is this value. And now integral is of dimension of simple function. It is convenient and conventional to, instead of the by frequency, introduce the by temperature by a very simple expression. The by temperature is h omega d divided by kb. You might think about multiplying by kb. Kb theta d is thermal energy corresponding to the by temperature, and it is equal to the energy, maximum energy of the phonon. This is mean of the by temperature. Now this ratio is ratio of the by temperature over thermodynamic temperature, because h omega d over kb is theta d, and I have 1 over t here. Of this expression, this integral I can denote as f. It's a function of dimensionless quantity, which is ratio of theta d over t. This function is called the by function. So what will be here? The third power of kb, third power of omega cube d, and third power of h give me theta d. So we're left with fourth power of t here and first power of kb. And it of course has correct dimensionality, because third power of temperature and the by temperature cancel, so it's kBt. bidimensionality. I will continue. I'm repeating the last formula. And obviously this function is nothing else as integral of this simple expression. And to some x is dimensionless quantity, which in formula for U, for free energy, is ratio of theta d over t. Now, I can tell that this function, very simple function, as strange as it may be, it is not expressible in terms of any other standard function of mathematical physics. Not gamma function, not beta function, not zeta function. It is a dependent transcendental function, and it is called the bifunction, named by name of Peter Debye, whose life history very shortly we'll mention after the end of this lecture, at the end of this lecture. So first thing first, let us understand behavior of this function. This function is a fundamental value for us. It describes the phonal contribution of acoustic phonon to thermodynamic quantities of a solid. And then we will continue and find the properties, these thermodynamic properties of the solid in the bimodal. So first thing first, we'll study it mathematically. We'll find asymptotic behavior. So we first consider x much less than 1. X much less than 1 in real life would be high temperature. So that would be classical case. So if x is smaller 1, then the z is also much smaller than 1. So expand this exponential. It expands to 1 plus z. 1 cancels. So z is left. So this integral of z squared, the limit from 0 to x, will give me x cubed over 3. So that would be low x limit, which will describe for us the classical limit of the gas. Opposite system, when the argument is very large, temperature is very small, it's quantum mechanical limit, extreme quantum mechanical limit. In this case, we can replace upper limit, which is very large, and this function very well converges because of the exponential. So with very good precision, is exponential precision, so the error would be exponentially small, I can replace it by infinity. Then it becomes standard function, is expressible in terms of the gamma function of factorial, and zeta, Riemann zeta function, and its value is pi to the 4 of 15. And it'll tell me that you already saw this number. You did see it in the theory of photons. Because when in these cases, see the maximum frequency can replace by infinity, and this is exactly the same for photons. So it is not surprisingly I got the same number that enters the theory as for photons. We made all the way back to photons. Let me wait a minute, and you can ask a question about this technical part, and then we'll continue with physical part. Let's move. So this is the bifunction. Just take any mathematical software as Mathematica. I plotted it. It's basically a precise plot. Error here is negligible, numerical error. So this is very simple curve. It doesn't have any singularity, is monotonous because integrand is positive. There's no singularity in this function. It's a very simple function. So it starts as a cubic parabola, x cubed over 3. It is here. It has inflection at value of argument on the order of 1. It changes its curvature. and ends with a constant. Very large values practically reach this constant at 10 is pi to the 4th or 15. Now I'm repeating the expression we got. So this is a general expression for internal energy in the bimodal. And now we'll consider limiting cases. So classical limit. Classical limit is when this argument is small, temperature much greater than the by temperature, this function is 1 over 3 cube of the argument. I substituted here. So third power of temperature eliminates. Third power of the by temperature eliminates. So the by temperature disappears from the result. This 3 cancel the 3 of 9, leaving only 3. So the U will be simply 3 and A kBt. Now we find CV. CV is derivative of U over T at a constant V. V is not a parameter. We nowhere have the volume of the crystal. So I can write it, but it doesn't matter. There's nothing to fix. What is actually fixed is number of atoms. So it will give me 3 Na Kb. And this is expression of equipartition because 3 Na is number of degree of freedom. It means that Cv is equal Kb for each degree of freedom, which we know for oscillations is statement of the equipartition theorem. So this is a classical limit. The classical limit equipartition theorem is satisfied automatically. Not so in quantum mechanical limit. So quantum mechanical limit is opposite limit. So t is small. Argument of this function is very large. So this function is a constant. Like for photons, it is pi to the 4 over 15. And u is equal. So 15 I will lose 3. I will be 3/5 pi to the 4th. kBt to the 4th. Nothing cancels. It's just a constant added. This constant. This constant which is pi to the 4 over 15. This formula, we get Cv. And this formula, by the way, is akin to Stefan-Boltzmann relation in theory of radiation and also first power of temperature. Correspondingly, Cv, I need to differentiate over T will give me an extra 3. So will give me T to the cube. Will give me here 9. And this is counterpart of the corresponding formula of blackbody radiation when thermal capacitance is cube of temperature. And for degree of freedom, Cv is equal, this one, is much less than kBt, much less by this very, very small factor. And this is what is called degeneracy. Now, question is whether the thermal capacitance of solids is really a cubic function of temperature. It's a very interesting question. So I can tell you the result. At very low temperatures, it's always cube. So this formula perfectly defines the behavior of solids at low temperatures. It's understandable. At low temperature, only very low frequency phonons are excited. They do not reach the boundary Brillouin zone, so the dispersion relation is perfectly linear. And how the curve ends, what is the second assumption of the bi, does not matter, because phonons never reach the end of the zone, never reach limiting frequency. Therefore, the expression works so well. One can ask what is actual value of the Debye temperature for real crystals. It depends whether this molecular crystal is ionic crystal, is covalent crystal. So the stronger is the bond, the lighter atoms, the higher the bite temperature. In practical terms, the bite temperature is somewhere from tens of Kelvin to thousands of Kelvin. Sometimes it's so large you cannot reach it. You will melt crystal or dissociate crystal before that. So it's a very wide energy for existing crystals. The bite temperature is important in many physical phenomena. Here I probably will mention some of them in the final part of this lecture, next part, that is devoted to history, which is very important to understand, both for science and also for yourself, because you will have to make many decisions in your life. Some of them may be not easy decisions. And the buyer lived, as I'll explain you, in the most demanding time. When it was the honest person it was very difficult for him to survive and do something positive, and he did it. So this I will be explaining you later. Just next slide. So let me finish at this point. You may ask me questions. I will give you, say, 5 minutes to go over the whole lecture. Let's move on. So, very brief biography of Peter Debye. Let you see his photograph. He was born in March 24, 1884 in Maastricht, the Netherlands, and died in 1966 in Ithaca, New York, where he was working at the Cornell University. He died at 82. He has dual citizenship, Netherlands, United States. He graduated from his undergrad degree was from the University of Aachen, Germany, and graduate degree from the University of Munich. He graduated under Arnold Sommerfeld. And by the way, Sommerfeld would say that his greatest discovery was discovery of Peter Debye. He is known for the Debye model, just discuss it. Debye relaxation, the textual relaxation constant that we gamma that we have in plasmonics, those who take also course plasmonics know it. Debye frequency, we just introduced it. He got numerous awards. 1930 Rumford Medal, Faraday Lectureship Prize, 1933 Lawrence Medal 35. He got Nobel Prize in Chemistry 1936. Wheeler Gibbs Award 1949. It's already after the war in the United States. Max Planck Medal, this highest award of the German it's German Physical Society, I would say. Priestley Medal 1963. National Medal of Science, the highest scientific medal in the United States. By the way, we have a living scientist living in Atlanta who also was awarded the National Medal of Science. So if you know him, you can tell me. Otherwise, I'll tell you that it is Mustafa Sayed, professor of chemistry of Georgia Tech and my very big friend. His fields are physics and chemistry, and he worked in numerous institutions in Europe. He changed them regularly and frequently. University of Zurich, Switzerland. Utrecht, it's the Netherlands. Göttingen is one of the premier universities in Germany. ETH Zurich, it's a technical university in Zurich. The University of Leipzig, Germany. Zurich, of course, is Switzerland. Leipzig, Germany. University of Berlin, Germany. University of Berlin, he actually occupied chair previously occupied by Albert Einstein after Albert Einstein immigrated to the United States. In 1940, he himself immigrated. That I already mentioned his doctoral advisor is Arnold Sommerfeld. I have a few outstanding doctoral students, particularly Sager and Scherer, Paul Scherer, or Paul Scherer, if I want. And unfortunately, I don't know these two. So these are eponyms. So they are phenomena carrying the Debye name. Debye shielding, we call actually Debye screening, is plasma semiconductor electrolytes. Actually, it is used in plasma electrolytes. In semiconductors, it's most often called Thomas Fermi screening, but it's exactly the same. Debye length is Thomas Fermi length in semiconductors, length for screening occurs. Debye model, we just got it. Also, Debye is a unit of electric dipole moment, which is 10 to the minus 18 CGS. Debye frequency, we just got it. Debye relaxation, those who are in plasmonic class knows this is gamma, which is in the relaxation of plasmons. Debye sheath, or we call it the Debye layer today, the Thomas Fermi layer, it's most important phenomena in semiconductors. It's a phenomenon in which you can separate charges. And in the metal, it's just angstrom, but semiconductor may be micron or nanometer. Scale depends on doping. And everything semiconductor occurs within this Debye layer. The Debye-Huckel equation, the Debye function, we just got it. The Debye-Scherer method, I cannot say too much. The Debye-Wöhler factor is the factor that gives you phonon-free line in spectroscopy, including Mossbauer spectroscopy. And there are very interesting things. There's a Debye planet, a minor planet. This Lorentz-Mean Debye theory, actually conventional called Mean theory, the theory of light scattering from small spherical particles. There's a crater named Debye. It's a lunar crater on the far side of the moon. So his actual birth name is Petrus Josephus Wilhelmus Debye, it's pronounced Debye in Dutch. So this is the his scientific life. I won't cite too much. Just I already told you that Sommerfeld took Debye with him to Munich, and there is a photograph with Sommerfeld and Debye, the same photograph. It belongs to the Deutsche Physikgesellschaft, Deutsche Physical, German Physical Society.